Alright, so in this video, we'll be breaking down one last major colligative property. So we looked previously at our boiling point elevation, freezing point depression, and vapor pressure lowering. And so in this video, we'll be looking at our fourth colligative property, and that's going to be osmotic pressure. Osmotic pressure. And so, well, firstly, what is it? Osmotic pressure is going to be the pressure needed to stop the flow of solvent molecules through a semi-permeable membrane into a solution. And so if you're familiar with the concept of osmosis from chemistry or even biology class, that should make some sense. And kind of also you can get from the name osmotic pressure, it's dealing with osmosis, right? So let's just kind of draw out a diagram to make this make a bit more sense. So this is kind of a common tube that we'll see with osmosis when we're talking about osmosis. So let's say that we have this sort of U-shaped tube, and separating both sides, both columns here, is going to be a semi-permeable membrane. Let's say on one side we just have pure water, and on this other side we have some solution. So let's say again, on this side is just pure water, and on this side is some solution, so we can draw some of those solute particles in here. And so naturally what is going to want to happen, or what is going to occur, is this water, this pure water, is going to want to diffuse across this semi-permeable membrane over to the other side with the solution. And this is done, or this happens so that, well, then both sides across this membrane will be of equal concentration, right? They will reach a state of equilibrium where both sides are of equal concentration. So if we were let this osmosis to occur, you would notice, if you just redraw this tube, again with and with our just pure water on this side and our solution on the other, and don't forget to draw the semi-permeable membrane, well, we'll see that the side that has all these solute particles, the solution, well, the water is going to diffuse from the water side, leaving less water here and more. Now you can see this sort of uneven distribution. Well, you have less of your pure water, which has diffused across the semi-permeable membrane by a process known as osmosis, and now these have reached a state of equilibrium where they're at equal concentration now. And so that is the very concept that is occurring. So then where does osmotic pressure come in? Well, if we are able to apply some pressure from this side, well, then that would push against these solvent particles, solvent molecules, in this case the water molecules, preventing them from being able to diffuse across the membrane by osmosis, right? So when we have the pure solvent on one side and the solution on the other, the water molecules naturally are going to want to move into the solution to dilute it, right? And to prevent that movement, you have to apply a certain amount of pressure to the solution side, and that pressure is what is called as osmotic pressure. So why is this happening? Well, the solvent molecules are always moving towards a higher concentration of solute, right? In order to balance out the concentrations, like I've already explained. And so when the solute particles are present, they sort of pull the solvent molecules in because there are fewer free solvent molecules on the solution side. And so in order to stop this movement, we're going to push back with pressure. And the pressure then that is opposing osmosis from occurring, that is what is your osmotic pressure. And so like the other colligative properties that we've explored, osmotic pressure can as well be quantified using a formula. And that is going to be this formula right here. Let me just clear this word osmotic pressure out of the way as well. We know we're talking about osmotic pressure. So that is going to be pi equals mRT and I, your Van Hoff factor there. And so this pi, that is going to represent your osmotic pressure, right? M here, that is actually, an uppercase M, and it's going to represent your molarity. Not to be confused with the lowercase m for molality, which we've seen come up with our other colligative properties like boiling point elevation and freezing point depression. Molarity is actually just going to be your moles of solute divided by liters of solution. On the other hand, molality, well, that is going to be moles of solute divided by kilograms of solvent. So these two are not equal to one another. They are distinct, units of concentration. So it's important that you know what is being used. And well, in this case, we have clearly a capital M, so that is our molarity, not molality. Next, you can see that we have, again, so this is moles over liters, again, of solute over solution. And your R here, that is going to be your ideal gas constant. Your ideal gas constant, which is going to be equal to 0.08206 liters times ATM over moles times Kelvin. And again, this can be further expanded depending on your formula sheet, but this is, sort of an abbreviated or cut down, rounded version of the gas constant. And you'll notice, again, the gas constant here, there's units of Kelvin, and so, as you may have guessed, your T here is actually temperature, and that temperature is going to be in Kelvin. It's going to have to be in Kelvin. And finally, our I, well, that is something that we've become quite familiar with looking at our colligative properties, right? That is going to be your Van 't Hoff factor. And again, colligative properties are very much dependent, but definitionally dependent upon the number of particles, right? That's why the Van 't Hoff factor is important. Let's say for NaCl, the example we've been talking about in all these videos, we know it dissociates into Na plus and Cl minus into 2 particles. And so the I, that Van 't Hoff factor for NaCl, is going to be 2. So it's important that you keep in mind exactly what the solute that you're using is and calculate the appropriate Van 't Hoff factor. In the case of non-electrolytes, something that doesn't dissociate into ions or separate particles, well, it's just going to be 1. And just to kind of make clear, let me just actually get rid of this just to make some space, but you can kind of see with our formula here that if we were to actually plug in values, well, our molarity, that's going to have units of moles per liter, times your gas constant, that's liters times ATM over moles times Kelvin. And finally, your temperature here is going to be in Kelvin. Your Van 't Hoff factor is unitless, so we're not going to include that here. But you'll notice that liters and liters and moles and Kelvin are going to cancel out. And that is going to leave you with an answer in units of ATM, which we know to be a unit of pressure. So it makes sense since we're finding osmotic pressure. So I kind of just wanted to demonstrate this here, just so you kind of see how it all comes together, and you'll notice that's how you can kind of keep in check as to what units you need to use, and make sure you don't make any mistakes that way, which is also just another reason why you should include your units at all parts of the steps so you don't get any confusion there. But again, you can get your answer in ATM because we're using the gas constant, but I'm sure you are familiar with the idea that you can obviously convert from ATM to any other unit of gas, right, or any other unit of pressure that you may want to have your answer in, whether it be torr or whatever you want. But this will yield an answer in ATM. So now let's just look at a quick example problem as we have been doing in these past few videos. Again, let me just remind you that I'm going to make another video in the future where I will just be going through more complicated colligative property problems, but in this one I'll just simply demonstrate kind of proof of the formula, proof of concept. Alright, here we're trying to find the osmotic pressure of a 0.2 molar NaCl solution at 25 degrees Celsius. So we're trying to find the osmotic pressure, so let's use that formula. Pi equals mRTI. We are given our molarity to be 0.2. We know our gas constant already to be 0.08206. And our temperature, well, this is 25 degrees Celsius, but as I've kind of clearly talked about by going over the units, we know that our temperature T needs to be in units of Kelvin. And so, well, we can get our units of Kelvin by simply taking our temperature in Celsius and to it adding 273. So in this case, that is simply 25 plus 273, or 298 Kelvin. So multiplied by 298. And finally, that Van 't Hoff factor. It's very important. Well, we know NaCl is not a non-electrolyte. We know that it dissociates into Na plus and Cl minus ions, those two particles, so our I is 2. That is our Van 't Hoff factor here. So we multiply by 2. And this here will give us an answer of about 9.77. And we just talked about this. It's going to be in ATM. So this is going to be our answer. This is the osmotic pressure of a 0.2 molar NaCl solution at 25 degrees Celsius. So hopefully you found some value out of this video. If so, please show your support by liking and subscribing, and let me know what you guys would like to see next in the comments below. And I'll see you guys in the next video.